the ocean has a history that most people never hear about. Not the history of the dinosaurs, not the age of the great whales, not the era of human exploration, but something far older and in many ways far stranger. The Paleozoic era, which lasted from roughly 541 million years ago to 252 million years ago, was the period when the ocean went from a world of microbes and soft-bodied drifters to a world of hunters, armor, claws, and the first genuinely complex ecosystems the planet had ever seen. Nearly 300 million years of ocean history, almost completely invisible to most people, and packed with creatures so unlike anything alive today that they can be difficult to picture even with a photograph of their fossils in hand. Most people, when they think about prehistoric ocean life, jump straight to the age of the dinosaurs, to mosasaurs and plesiosaurs and the dramatic reptilian predators we covered in episode 4. But the Paleozoic ocean came first, and in many ways it was stranger, more experimental, and more biologically creative than anything that followed. The creatures that lived in it were not failed prototypes or primitive ancestors. Many of them were fully realized, highly effective predators and prey, operating in complex ecosystems that functioned successfully for hundreds of millions of years before being swept away by the most catastrophic extinction event in the history of life on this planet. This episode tells the story of the most remarkable of those creatures. Anomalocaris, the apex predator of the Cambrian seas, sometimes described as the first great predator in the history of complex life. Dunkleosteus, the armoured giant of the Devonian, whose bite force may have been the most powerful of any fish that has ever lived. The sea scorpions of the Silurian and Devonian, some of them growing to over 8 feet in length, hunting in shallow coastal waters at a time when nothing on land was large enough to challenge them. The nautiloids, ancient relatives of the modern nautilus, whose coiled and straight-shelled forms dominated the open ocean for tens of millions of years before their descendants were eventually replaced by more familiar ocean creatures. These are not obscure footnotes in the history of life. They are the main characters of a story that ran for nearly 300 million years. And understanding them means understanding something fundamental about how the ocean works, through cycles of innovation, competition, arms races between predators and prey, catastrophe and reinvention. The Paleozoic ocean set the ecological patterns that the Mesozoic and modern ocean would later follow. The specific animals changed with every mass extinction and recovery. The underlying structure, the logic of how an ocean ecosystem organizes itself, was worked out in the Paleozoic and has never been fundamentally revised since. We will travel through the Paleozoic period by period in this episode, meeting the dominant creatures of each era and tracing the dramatic changes in ocean life across nearly 300 million years. We will end at the Permian extinction, the catastrophic event that closed the Paleozoic era and came closer to ending all life on Earth than any event before or since. An event so severe that the ocean that came after it was, for millions of years, almost unrecognizable from the one that had existed before. The Paleozoic ocean did not end quietly. Understanding how it ended and how life survived that ending sets the stage for every episode in this series that follows. We will also spend time on what the Paleozoic ocean can teach us about the present. The patterns of extinction and recovery that played out across nearly 300 million years of Paleozoic history have direct relevance to what is happening in the ocean today. The relationship between rapid environmental change and mass extinction that defines the Paleozoic record is a relationship the modern ocean is currently navigating in its own way. The Paleozoic ocean was the proving ground. Every ecological strategy, every predator-prey dynamic, every cycle of catastrophe and renewal that has followed was first tested there. The story of the Paleozoic ocean begins with an explosion. Not a literal one, but something close to it in biological terms. About 541 million years ago, at the very start of the Cambrian period, the ocean underwent one of the most dramatic transformations in the history of life. We touched on the Cambrian explosion in episode 1, but in the context of this episode, it deserves a closer look, because it is the moment the Paleozoic ocean truly began, and the creatures that appeared in it set the stage for everything that followed in the hundreds of millions of years after it. Before the Cambrian, the ocean was dominated by the Ediacarans we met in the Snowball Earth episode. Flat, soft-bodied, frond-like or disc-shaped organisms that largely sat on the seafloor or drifted in the water column. They had no eyes, no hard shells, and no teeth. The ocean they lived in was peaceful in a way that the later Paleozoic ocean absolutely was not, because there was almost nothing in it capable of actively hunting anything else. The ecological dynamic was defined by absorption and growth, not by pursuit and capture. Then, in a geologically brief period, the rules changed completely. Animals with eyes appeared. Hard shells and external coverings appeared. Claws, mouths, and the ability to actively pursue and capture prey all appeared within what amounts to a geological instant. The entire ecological dynamic of the ocean shifted from passive to active. Predator and prey relationships, which would drive the evolution of almost every animal on Earth for the next 500 million years, began in earnest during the Cambrian explosion, and the ocean has never returned to its pre-Cambrian state of relative peace. The most dramatic predator of the Cambrian ocean was Anomalocaris, a creature we introduced in episode 1, but that deserves fuller treatment here. Anomalocaris could reach lengths of around 3 feet, making it the largest animal alive at the time by a significant margin. It had large compound eyes, a circular jaw-like structure made of overlapping plates capable of crushing hard-shelled prey, and a pair of grasping appendages at the front of its body that it used to catch and hold onto animals before feeding on them. For the organisms sharing the Cambrian ocean with it, Anomalocaris was essentially a monster, an animal so much larger and more capable than anything around it that it had no real competition at all in its time. The Cambrian ocean also produced a remarkable range of other creatures. Trilobites, the hard-shelled arthropods that would become one of the most successful animal groups of the entire Paleozoic era, made their first appearance in this period. They came in hundreds of species, from tiny reef dwellers to larger open-water swimmers, and they would persist in the ocean for nearly 300 million years before finally going extinct in the Permian. Hallucigenia, with its rows of spines and pairs of legs, looked so strange that scientists initially reconstructed it upside down and back to front because they could not work out which end was the head. The Cambrian Ocean was a world where evolution was running every experiment it could think of simultaneously. The Cambrian explosion was also the moment when the ocean first became genuinely dangerous to live in. Before predators with hard parts appeared, the ocean was a relatively peaceful place. Afterward, every soft-bodied organism needed a survival strategy, whether a hard shell, a burrowing habit, camouflage, speed, or chemical defenses. The ocean has been an arms race ever since, and understanding the Cambrian means understanding the engine that has driven the history of ocean life for the past 500 million years. The ocean has never returned to its pre-Cambrian state of relative peace, and no subsequent event has reset it back to a passive world. Diversity does not accumulate slowly and steadily over time. It explodes when conditions create opportunity, filling ecological space rapidly with experimental forms, most of which fail, but some of which establish new permanent lineages. After the Cambrian came the Ordovician period, lasting from roughly 485 to 443 million years ago. By this point, the Cambrian experiments had largely been sorted out. The body plans that worked had survived and diversified. Those that did not had disappeared. The Ordovician Ocean was more structured than the Cambrian, more divided into clear ecological roles, and more recognizable as a functioning marine ecosystem, at least in its basic organization. It was also, by the standards of what had come before it, extraordinarily diverse, with more species of marine animals alive at the same time than the ocean had ever contained. The dominant large animals were the nautiloids. These were ancient relatives of the modern nautilus, animals with shells and a body plan so effective that the nautilus itself, barely changed, is still alive today. The nautiloids of that time were far more varied than their modern descendants. Some had coiled shells like the nautilus we know today. Many had long, straight, conical shells that could reach impressive lengths, with some species growing to over 6 feet. They were the apex predators of the Ordovician, swimming through the water using jet propulsion, seizing prey with their tentacles, and dominating the open water environment in a way that no animal had done before them. The Ordovician Ocean was also the time when the first vertebrates, animals with backbones, began to appear and diversify. These early vertebrates were jawless fish without the ability to bite in the way modern fish do, but able to filter feed from the water or rasp material from surfaces. They were not the dominant animals of their time by any means, but their appearance at this time is significant because it marks the beginning of the vertebrate story that eventually leads to sharks, to fish, to the marine reptiles of episode 4, to whales, and ultimately to human beings. Every vertebrate alive today traces its ancestry back to these jawless fish. The Ordovician saw the first significant development of coral reefs. Earlier reefs had existed, built by sponges and other organisms, but this time period produced the first reef systems built substantially by coral-like organisms, creating underwater structures that concentrated biodiversity and provided shelter and hunting grounds for the growing variety of marine life. The basic concept of the coral reef, a structure built by small colonial animals that creates complex habitat for hundreds of other species, was established during this period and has been one of the most persistent and successful ecological strategies in the history of the ocean, surviving every mass extinction since. The earliest evidence of biological arms races in the ocean was during the Ordovician time. This was the evolutionary dynamic where predators and prey push each other to develop increasingly sophisticated offensive and defensive adaptations. shell thickness in brachiopods, and mollusks increased in ways that appear to directly track the development of more effective predators. The visual systems of trilobites became more complex during this period, with some species developing highly sophisticated, compound eyes capable of seeing in 3 dimensions. These are the signatures of an evolutionary competition played out over millions of years, of exactly the type that has driven complexity in ocean life ever since. The Ordovician ended in disaster. Around 443 million years ago, a major ice age struck. Sea levels fell dramatically, ocean temperatures dropped sharply, and the result was mass extinction, the second largest extinction event in the history of life on Earth, which wiped out roughly 85% of all marine species. The nautiloids lost many of their species. The trilobites were significantly reduced. The first coral reefs were devastated. When conditions eventually recovered, the ocean that rebuilt itself in the Silurian would be a substantially different place from the rich, diverse world that had existed before the freeze. But life, as it always does, came back. The Silurian period, which lasted roughly 21 million years, was in some ways the ocean's recovery phase after the end Ordovician extinction. Life came back, diversified, and in some respects became more complex and more dangerous than it had been before. The Silurian Ocean is the period when several of the most fascinating groups of Paleozoic sea creatures reached their peak, and it gave rise to one of the strangest and most impressive groups of animals ever to have inhabited the sea: the Eurypterids. Sea scorpions, formerly known as Eurypterids, were not actually scorpions in the modern sense, though they were distant relatives of scorpions and other arachnids. They were arthropods, animals with a hard external skeleton and jointed legs, related to the group that also includes crabs, lobsters, and insects. What set the Eurypterids apart from their relatives was their size. The largest Eurypterids ever found, belonging to a species called Dunkleosteus renaniae, discovered in Germany, may have reached lengths of over 8 feet. That is larger than most adult human beings at all, and it was moving through shallow coastal water on 6 pairs of jointed limbs, with large grasping claws at the front of its body. The Eurypterids had a flat, segmented body, large paddle-like rear limbs used for swimming, and in the larger species, a pair of substantial grasping claws that they used to catch and hold prey before consuming it. Their eyes were positioned on the top of their head, giving them a wide field of vision for detecting movement above and around them in the water. Some species appear to have been capable of moving onto land for short periods, which would have made them among the very first animals capable of crossing the boundary between water and land, making brief excursions onto a shore that as yet had nothing large enough to threaten them. The Eurypterids were not alone in making the Silurian Ocean dangerous. Jawless fish continued to develop during this period, many of them armoured with bony plates covering their heads and the front part of their bodies, an adaptation that suggests they were under significant predation pressure. The first jawed fish appeared during the Silurian, a development of enormous significance. The jaw is one of the most powerful innovations in the history of vertebrate evolution. It transformed fish from passive filter feeders or grazers into active hunters capable of seizing and processing prey in entirely new ways, and it set the stage for the explosive diversification of jawed fish that would follow in the Devonian period. Coral reefs expanded and diversified significantly, becoming more complex and varied than the Ordovician reefs that had preceded them. The Silurian Ocean was, in ecological terms, becoming increasingly structured and layered, with clear predator-prey relationships, specialized feeding strategies, and ecological niches being defined and contested in ways that would look familiar to a modern marine biologist, even though the specific animals occupying those niches were entirely unlike anything alive today. The sea scorpions hunting in the shallows, the nautiloids cruising in the open water, the armoured jawless fish hovering near the seafloor, each occupied a distinct ecological role in a system of growing complexity. The Silurian period also produced some of the earliest evidence that life was beginning to seriously test the boundary between water and land. Plants were establishing themselves in coastal environments. Early arthropods were making excursions onto damp soil. The world was, for the first time, beginning to have a land surface worth inhabiting, and the Silurian Ocean was the ecological base from which that colonization of the land slowly proceeded. The ocean has always been the origin point of life on Earth, and the Silurian is one of the clearest moments where the relationship between the sea and the emerging land can be seen actively playing out for the first time. The Devonian period, lasting from roughly 419 to 359 million years ago, is sometimes called the Age of Fish, and for good reason. During this period, fish diversified more rapidly and more dramatically than at any earlier point in their history, filling almost every ecological niche the ocean had available and producing a range of forms that would not look out of place in a science fiction film. The Devonian Ocean was warm, largely shallow, and extraordinarily productive, conditions that provided an ideal environment for an explosion of aquatic life that would eventually reach every corner of the sea. The most successful and visually striking fish of the time were the placoderms. The word placoderm means plated skin, and the name accurately describes their most notable feature: a heavy armour of interlocking bony plates covering the head and the front portion of the body. This armour served as protection against predators, but it also created a significant structural challenge, because armour is heavy and inflexibility is a disadvantage when swimming. Placoderms dealt with this through an unusual solution. Rather than having a lower jaw that dropped, the way virtually all modern jawed animals do, placoderms had an upper jaw that lifted. The entire front of the head could hinge upward, opening the mouth from the top as well as the bottom and creating an extremely wide gape with very little effort. Placoderms ranged enormously in size and lifestyle. Some were small, flattened bottom dwellers that fed on invertebrates on the seafloor. Some were mid-water hunters of modest size, and some were giants, powerful, heavily armoured predators operating at the top of a very competitive food chain in an ocean that rewarded size and aggression in a way few earlier periods had done. The Devonian Ocean, with its warm, shallow seas and abundant prey, was exactly the kind of environment in which large, heavily built predators could thrive, and the placoderms took full advantage of it for millions of years. The Devonian also saw the continued evolution of sharks and the first appearance of lobe-finned fish, the group that would eventually give rise to the first land vertebrates. The first animals with 4 limbs, the tetrapods, made the transition from water to land during the late Devonian, a development that would eventually lead to amphibians, reptiles, mammals, birds, and every other land-dwelling vertebrate on Earth. This ocean was not just an extraordinary environment in itself. It was the launching pad for the colonization of the land, and the creatures that made that transition were products of the biological richness the Devonian Sea had generated. The variety of life in a Devonian reef environment would have been overwhelming to a modern observer. Armored fish of all sizes competing for territory and prey. Early sharks weaving between them. Lobe-finned fish lurking in shallow water near the shore, some of them already developing the proto-limbs that would eventually carry their descendants onto dry land. Crinoids, sea lilies related to modern starfish and sea urchins, carpeting the seafloor in dense colonies of feathery arms. Brachiopods filtering nutrients from the water. Ammonites, the coiled cephalopods that would later come to define the Mesozoic Ocean, making their first significant appearance. This ocean was a fully realized, multi-layered ecosystem of staggering richness and variety. The Devonian is also notable for producing some of the most scientifically important fossils ever found. Tiktaalik, a fish discovered in the Canadian Arctic in 2004, lived during the late Devonian and displayed features intermediate between fish and tetrapods, including a neck, a flattened head, and fins with internal bone structures similar to a primitive limb. It is one of the most celebrated transitional fossils in the history of paleontology, and it was a product of exactly the kind of shallow coastal Devonian environment we have been describing. It shows, in preserved bone, the moment when the ocean was preparing to release its creatures onto the land. Among all the extraordinary animals of the Devonian Ocean, one stands above the rest in terms of sheer physical impact and predatory power. Dunkleosteus torelli was a placoderm fish that could reach lengths of around 20 feet and is estimated to have had one of the most powerful bites of any fish that has ever lived. It was, by most measures, the apex predator of the late Devonian Ocean, and it was a genuinely intimidating animal, even by the standards of an era that produced no shortage of large, aggressive, heavily armoured predators competing at the top of a rich food chain. Dunkleosteus did not have teeth in the way most predatory fish do. Instead, its bony head armour extended forward into sharp, self-sharpening bony blades that functioned like teeth but were actually extensions of the skull itself. These blades were continuously honed by the upper and lower surfaces, grinding against each other as the mouth opened and closed, ensuring that they always had razor-sharp cutting edges available. Scientists studying its bite mechanics have estimated that it could open its mouth from fully closed to fully open in approximately 20 milliseconds, faster than most animals can react, and that the suction force created by this rapid opening would pull water and prey into the mouth, even before the jaws closed. The bite force has been estimated at over 8,000 pounds per square inch in the most powerful species. The evidence that Dunkleosteus was eating other armoured fish comes directly from the fossil record. Sites have been found containing what paleontologists call regurgitation masses, concentrations of partially digested bone fragments that Dunkleosteus appears to have coughed up after feeding, similar to the pellets that owls produce today. Those bone fragments include the skull and jaw elements of other large placoderms, confirming that Dunkleosteus was not just capable of eating armoured fish, but was regularly doing so. It was the top predator in a food chain that itself consisted primarily of large, heavily armoured animals. The fact that it was eating those animals with apparent regularity tells us something important about just how effective its jaws were. The fossil record for Dunkleosteus is concentrated in what is now Ohio, which was at that time a shallow tropical sea sitting near the equator. The sheer number of fossils found in that region suggests it was a common animal in that environment, which in turn tells us something important about how productive and food-rich the late Devonian Sea must have been. An apex predator does not become common without an enormous base of prey supporting it at every level of the food chain below it. The Devonian Ocean was clearly capable of producing that base in abundance, and Dunkleosteus was the beneficiary. Dunkleosteus also illustrates the Devonian Ocean's defining evolutionary dynamic, the arms race between predator and prey. The heavy armour of placoderms was not there by accident. It was the product of millions of years of predation pressure, an evolutionary response to living in an ocean where being bitten hard was a regular occupational hazard. The competition between protection and power, between the thickness of a prey animal's covering and the strength of a predator's jaws, runs through the entire history of complex ocean life and is just as visible in the modern ocean as it was 375 million years ago. The crab's hard shell, the clam's thick valve, the nautilus's coiled exterior are all products of the same ancient selection pressure that drove Dunkleosteus and its prey to their respective extremes. The end of Dunkleosteus and the placoderms came at the close of the Devonian period, around 359 million years ago, when a series of extinction pulses struck the ocean. The causes are still debated, but they likely included rapid changes in ocean chemistry and the carbon cycle disruptions driven by the spread of forests on land. Whatever the precise combination of factors, the placoderms were completely wiped out. Not a single species survived into the Carboniferous. An entire major group of vertebrates, one that had dominated the ocean for over 60 million years, was erased entirely. The sharks that had been sharing the Devonian Ocean with them survived. The placoderms did not. After the Devonian extinction, the ocean entered a new phase. The Carboniferous period, lasting from roughly 359 to 299 million years ago, and the Permian period that followed it, from 299 to 252 million years ago, together make up the later half of the Paleozoic era. These were periods of significant change, both in the ocean and on the land, and the marine life of the Carboniferous and Permian tells a somewhat different story from the exotic giants of the Devonian, quieter in terms of dramatic individual animals, but no less significant in terms of building the biological world that would follow. The Carboniferous Ocean was in many ways a transitional environment. The placoderms were gone, and the ecological space they had occupied was now available to be filled. Sharks, as we discussed in episode 5, expanded dramatically during the Carboniferous into those vacated niches, producing an extraordinary variety of forms, including some with body shapes and tooth structures that have no modern equivalent. The Carboniferous is sometimes called the Golden Age of Sharks by paleontologists, and the fossil record from this period reflects that description with an impressive array of shark forms occupying ecological roles that modern sharks do not hold. The invertebrate communities of the Carboniferous Ocean were dominated by groups that had survived the Devonian extinctions and diversified in their aftermath. Crinoids, the sea lily-like animals that filter feed from the water using their feathery arms, reached perhaps their greatest abundance and diversity during the Carboniferous, carpeting shallow seafloors in dense colonies that could extend for miles. The limestones of the American Midwest, which were laid down during the Carboniferous, when that region was covered by a warm, shallow sea, are packed with crinoid fragments so densely in some layers that the rock is made almost entirely of their skeletal material. The scale of life in the Carboniferous shallow seas was staggering. Ray-finned fish, the group that today accounts for roughly half of all vertebrate species on Earth, including virtually all the fish most people are familiar with, from salmon to tuna to goldfish, began their major diversification during the Carboniferous. The ocean was in many ways building the biological foundations of the modern marine world, assembling the major groups of fish, invertebrates, and other organisms whose descendants would eventually populate the post-Paleozoic seas. The Carboniferous Ocean was less dramatic than the Devonian, but arguably more important because it was producing the raw material for everything that would follow. The Carboniferous is also notable for what was happening at the level of ocean chemistry and atmospheric composition. The vast coal forests of the Carboniferous were removing CO2 from the atmosphere in enormous quantities, and the oxygen levels in the atmosphere during this period were significantly higher than they are today, perhaps 35% compared to our current 21%. Higher atmospheric oxygen meant higher dissolved oxygen in the ocean, which supported more active and energetically demanding forms of marine life. Some scientists believe this elevated oxygen level contributed to the large body sizes seen in some Carboniferous invertebrates. Oxygen availability sets fundamental limits on how large and how metabolically active an animal can be, and the Carboniferous atmosphere temporarily pushed those limits upward in ways that left clear marks in the fossil record. The Carboniferous and Permian periods together lasted for over 100 million years, nearly as long as the entire span of time from the extinction of the dinosaurs to the present day. They were not a coda to the Paleozoic. They were a substantial chapter in their own right, building the biological complexity that would make the Permian Ocean, in many respects, the most diverse and ecologically sophisticated the Paleozoic had ever produced, right up until the moment it was destroyed. The Permian period, the final chapter of the Paleozoic era, lasted from roughly 299 to 252 million years ago. In many respects, it was the Paleozoic ocean at its most mature. The ecological roles established in earlier periods had been refined and optimized over hundreds of millions of years of continuous evolution. The major groups of marine organisms were well established and widespread across the global ocean. The food web was complex, the reef systems were extensive, and the diversity of marine life was extraordinary. It was also sitting on the edge of the greatest catastrophe in the history of life. The Permian Ocean was dominated by many of the same groups that had characterized the later Carboniferous. Sharks were abundant and varied. Ray-finned fish were continuing to diversify. Crinoids and brachiopods continued to be major components of seafloor communities, covering large areas of the ocean bottom in dense, filter-feeding colonies. Ammonites were expanding their range and diversity. coral reef systems rebuilt after the Devonian extinction were extensive and biologically rich. The ocean itself was doing what it had always done, supporting an extraordinary web of life with every level of the food chain occupied by a wide variety of specialized animals going about their business. One group of Permian marine animals deserves particular attention because of how dramatically their story would end. The trilobites, those hard-shelled arthropods that had first appeared in the Cambrian and had been a continuous presence in the ocean for nearly 300 million years, were still alive during the Permian, though reduced in diversity compared to their earlier peak. They were one of the most enduring success stories in the history of life on Earth. Animals that had navigated the Ordovician extinction, the Devonian extinction, and the end Carboniferous changes, always finding a way to survive and recover. The Permian would be their final chapter, ending a lineage that had been part of the ocean longer than any other complex animal group. What ended the Permian, and with it the entire Paleozoic era, was an event so catastrophic that scientists have given it a specific and grim name: the Great Dying. Around 252 million years ago, a series of volcanic eruptions in what is now Siberia released an almost unimaginable quantity of carbon dioxide and other gases into the atmosphere over a period of perhaps a few 100,000 years. The result was severe global warming, combined with ocean acidification, the collapse of oxygen levels in large parts of the ocean, and changes to ocean circulation that disrupted nutrient cycles globally. The ocean simultaneously became hotter, more acidic, and less oxygenated, and it did so faster than most marine species could adapt to. The numbers are staggering. Up to 96% of all marine species went extinct during the Permian extinction. The trilobites were completely wiped out. The blastoids disappeared entirely. The rugose corals and tabulate corals, which had built the reef systems of the Paleozoic, went extinct and would be replaced in the Mesozoic by the scleractinian corals, whose descendants build reefs today. The ocean that emerged from the Permian extinction was, in biological terms, almost unrecognizable from the one that had existed before. It was not empty. Life survived, as it always does. But it took millions of years for the ocean to rebuild anything approaching the complexity and diversity it had lost. The recovery from the Permian extinction was the slowest of any major extinction recovery in the Paleozoic record. Estimates suggest it took between 5 and 10 million years before ocean diversity began to recover significantly. This slow recovery tells us something important about the difference between the survival of individual species through a catastrophe and the reconstruction of the complex ecological relationships between those species that constitute a functioning ecosystem. Species surviving is necessary but not sufficient. Rebuilding the relationships between those species, the food chains, the competitive dynamics, the symbioses, takes far longer. The Permian extinction ended the reign of several of the most characteristic and enduring groups of the Paleozoic ocean permanently, and their absence shaped everything that followed. The Paleozoic ocean lasted for nearly 300 million years. To put that in perspective, 300 million years ago, there were no dinosaurs, no flowers, no birds, no mammals, and no humans. The entire span of time that has passed since the Permian extinction, including all of the Mesozoic and the modern era, is shorter than the Paleozoic era itself. It was not a brief or minor chapter in the history of the ocean. It was a vast, complex, and largely self-contained world that rose, matured, and ended all before anything we would recognize as the modern ocean had yet come into existence. What does the Paleozoic ocean teach us? First, and most fundamentally, it teaches us about the power of ecological experimentation. The Cambrian explosion established that when conditions allow for it, life does not settle into a single stable configuration. It tries everything. Most experiments fail, but the ones that succeed shape the world for hundreds of millions of years afterward. The basic ecological roles established in the Paleozoic ocean, apex predator, mid-level hunter, filter feeder, bottom dweller, scavenger, are the same roles that structure the modern ocean. The specific animals filling those roles have changed completely. The roles themselves have not. Second, the Paleozoic ocean teaches us about resilience and its limits. Life survived the end Ordovician extinction. It recovered from the late Devonian extinction. It persisted through the end Carboniferous changes. Each time, it diversified and rebuilt the complexity it had lost, sometimes producing ecosystems more diverse than the ones that had existed before the catastrophe. But the Permian extinction pushed beyond what recovery could accommodate in any reasonable time frame. The 96% marine species loss was not just a reset of the ocean, it was close to an erasure, and the ocean that rebuilt itself in the Triassic was a fundamentally different structure from the Paleozoic world it replaced. Third, and perhaps most relevant to the present, the Paleozoic ocean shows us what happens when the pace of environmental change exceeds the ability of life to adapt. The Permian extinction was caused by rapid, large-scale changes to ocean chemistry and temperature driven by geological processes. The changes were not gradual enough for most species to evolve responses to them. Life is adaptable, but adaptation requires time. When the environment changes faster than evolution can respond, extinction follows. That relationship between the pace of change and the capacity for adaptation is not ancient history. It is the central challenge of ocean conservation in the present day, and the Permian extinction is the clearest illustration in the geological record of what happens when it goes wrong. The Paleozoic ocean also leaves us with a specific and humbling message about scale. The entire span of recorded human history, roughly 5,000 years, is less than 1/10 of 1% of the time the Paleozoic era lasted. The geological processes that shaped the Paleozoic ocean operated on timescales that make human civilization seem instantaneous. And yet, the extinction at the end of the Paleozoic, the event that ended 300 million years of ocean history, was driven by processes that operated over mere hundreds of thousands of years, brief by geological standards. The ocean can be changed quickly relative to its own deep history. It has happened before. The Permian extinction is the evidence. The creatures of the Paleozoic ocean are mostly gone. The trilobites that crawled across sea floors for 300 million years. The sea scorpions that hunted in shallow coastal waters. Dunkleosteus and its armoured kin. Anomalocaris, the first great predator of complex animal life. They are gone, and the ocean they lived in is gone with them. But the patterns they established, the ecological logic they developed, and the biological innovations they pioneered are still present in the ocean today, carried forward by the lineages that survived. The Paleozoic ocean reminds us that history is not a progression from primitive to advanced. The trilobite that crawled across a Cambrian seafloor was a highly successful animal that filled its role for nearly 300 million years. By that measure, it outperformed almost everything that has come since. The Paleozoic ocean was not a prologue. It was a complete story in its own right, nearly 300 million years of life, as rich and complex and dramatic as anything that followed. Understanding it means understanding that the modern ocean is not the first version of itself. It is the latest iteration of a story that has been running, with interruptions, for over 500 million years. In our next episode, we follow the story of how whales, animals that evolved entirely on land, made one of the most remarkable journeys in the history of life by returning to the sea. From hoofed mammals on a beach in ancient Pakistan to the largest animals on Earth. Until then, thank you for listening.